The integer 1728 is built into the normalization of the modular J-invariant, a central pillar of complex geometry. Exactly one digit away sits 1729, the hardy Ramanujan taxicab number, the smallest integer representable as a sum of two positive cubes in two distinct ways. Because these numbers are adjacent on the number line, popular accounts often assume they belong to the same mathematical phenomenon. This proximity suggests Ramanujan's taxicab number is deeply intertwined with the modular world defined by 1728. Proximity in integers does not imply a shared mathematical identity. In the case of 1728 and 1729, this adjacency masks a structural fracture. These two integers represent divergent geometric realities that operate by entirely different rules. To understand the difference, we must look at the underlying Diophantine equation of the taxicab problem, x cubed plus y cubed equals d. A Diophantine equation is a polynomial equation where we specifically seek integer or rational solutions. The smooth projective closure of this cubic equation defines a genus 1 curve. A smooth projective closure is a geometric process of adding points at infinity to ensure the curve is a complete, unbroken loop. Once a rational base point is chosen, this curve is classified as an elliptic curve. By mapping this cubic equation into the coordinate system of complex elliptic curves, we can determine exactly where the taxicab equation lives in the broader landscape of geometry. Ramanujan's taxicab phenomenon is not a matter of numerology. It possesses a distinct architectural address within the complex moduli space. The classical modular J function is the principal invariant for elliptic curves over the complex plane. Two curves are isomorphic, meaning they have the same structure, if and only if they share the same J-invariant. This plane represents the coarse moduli space. A coarse moduli space is a geometric map where every point corresponds to a distinct isomorphism class of complex elliptic curves. The J-invariant acts as the definitive coordinate system for this map. The coordinate j equals 1728 corresponds to a curve with complex multiplication, an arithmetic property where the curve's endomorphism ring is larger than the integers. In this specific case, the coordinate represents a curve derived from a perfectly uniform square lattice. The coordinate j equals 0 represents the second maximally symmetric lattice type, the equion harmonic or hexagonal lattice. These two coordinates mark the primary symmetry points of complex elliptic geometry. Locating the taxicab curve requires determining which of these two fundamental types it corresponds to. We return to the cubic equation x cubed plus y cubed equals d to determine its coordinates on the moduli space. We can analyze this through birational equivalence. A birational equivalence is a transformation that maps one curve to another using rational functions, proving they are geometrically identical despite their different algebraic forms. We apply specific rational substitutions. Capital X equals 12d divided by x plus y, and capital Y equals 36d times the quantity x minus y divided by x plus y. We test these substitutions against the standard elliptic curve form, y squared minus the quantity x cubed minus 432d squared. Expanding the algebraic expression yields a fraction with the following numerator, 1728d squared, multiplied by the quantity x cubed plus y cubed minus d. Because the curve is defined by the condition that x cubed plus y cubed equals d, the expression x cubed plus y cubed minus d is exactly 0. This causes the entire expression to vanish identically, completing the proof. The cubic curve x cubed plus y cubed equals d is birational over the rationals to the Weierstrass model, y squared equals x cubed minus 432d squared. This is the short Weierstrass form, the standard template used to calculate the J-invariant for any elliptic curve. When we align our taxicab curve with this template, the coefficients become clear. Our taxicab curve has no x term. In this Weierstrass model, the coefficient a is exactly 0. We now apply the standard formula for the J-invariant, which is 1728 times 4a cubed divided by 4a cubed plus 27b squared. Since a is 0, the numerator becomes 0, and the entire expression collapses. The J-invariant is 0. This reveals the geometric reality. The entire family of taxicab equations sits in the j equals 0 equi and harmonic sector, structurally separated from the j equals 1728 sector. We can now apply this general theorem to Ramanujan's specific integer, 1729. Setting d to 1729 defines the specific elliptic curve E sub 1729. We take the first taxicab representation, 1 cubed plus 12 cubed, and process these values through our birational transformation. The transformation yields the coordinate 1,596, negative 52,668. This is an explicit point on the Weierstrass curve. We repeat the process for the second representation, 9 cubed plus 10 cubed, which yields the coordinate 1,092, negative 3,276. Ramanujan's cube decompositions are not merely arithmetic curiosities. They are explicit rational points on a j equals 0 elliptic curve. The proximity of 1728 and 1729 on the number line does not imply a shared geometric structure. 1728 marks the coordinate of a square lattice complex multiplication point. 1729 marks a significant arithmetic event on a cubic twist family, which corresponds to the hexagonal lattice. These integers signify two entirely different modular environments. Moving from 1728 to 1729 involves a sharp turn in the geometry of complex moduli. The history of these two disparate geometric worlds meets in the career of Srinivasa Ramanujan. Ramanujan's work on modular equations and singular moduli placed him in the domain where the J-invariant is the central classifier. Simultaneously, his observation regarding 1729 connected his name to the arithmetic of sums of cubes and Diophantine representation. These two domains, the analytic classification by J and the arithmetic study of cubic curves, are not separate. They are both parts of the theory of elliptic curves. Ramanujan's work bridges the analytic classification of modular forms and the arithmetic of cubic curves, showing that these apparently distinct areas of number theory are connected through the geometry of elliptic curves.